Hi everyone, welcome back to 3 Deviations. In today's video, we want to talk about the second derivative test. Now, I'm sure you're getting all this deja vu from single variable calculus because so far in this unit, we've basically been doing a rerun of our derivatives and applications of derivatives units because that's really what we're doing. We're just expanding what we learned to multivariable functions. So in today's video, we want to talk about the second derivative test. So in the last video, we talked about maxima and minima of two variable functions. So what's important about that is that we found that it was quite challenging to determine the physical meaning of a critical point. We know how to find the critical points. That's when both partial derivatives are equal to 0. But in order to actually interpret that, we needed to look more into the function. So luckily, in the last video, our function was a paraboloid. But our functions aren't always going to be paraboloids, so we need some more tools to determine what our critical values actually are. So that's why we are going to use the second derivative test to determine what our values actually are. And we don't need a sign chart here. We only need to use a very comprehensive test that I am going to show you in this video. So let's get started with the second derivative test. The definition of the second derivative test states that if derivatives exist, so partial derivatives with respect to x and y, exist on a disk centered at a comma b, and at a comma b, the partial derivatives with respect to both x and y are equal to 0, then we can define some capital D such that d of a and b is equal to the second partial derivative with respect to x both times of a and b, at a and b, times the partial derivative taken twice with respect to y at a and b, minus the square of the partial derivative with respect to x then y, or y then x, whichever you like, at a then b. Of course, we covered earlier that if I have my second partial derivatives, if I have partial x, partial y, or partial xy and partial yx, those are equal to one another. So we can use them interchangeably. Now, a way to remember this can be written as a determinant, right? Because we have AD minus BC, and of course the B and the C are the same, so we square it. So I could write this as here partial x squared, then on the other diagonal partial y squared, then partial xy, then partial xy, or partial yx. You can use that interchangeably. We want to take the determinant of this matrix, and that's what we get right there. Okay, so from this we get three cases, or four cases really. So in the case where d is greater than 0, and our partial derivative with respect to x taken twice at a comma b is larger than 0 as well, then f of ab will be a local minimum of our function. If the d value is greater than 0, but the partial derivative taken with respect to x twice at a comma b is less than 0, then f of ab is going to be a local maximum. If d is less than 0, and if d is less than 0, then f of a comma b is going to be called a saddle point. Now, what is a saddle point? Now, a saddle point is when I have, let's say I have a function. This comes across in physics a lot where you have potentials, but say I have this kind of quartic potential here. It looks kind of like a, I don't know what that looks like. But anyways, this is a very common potential well that you have. I think in the Higgs field it's very common. But anyways, if we rotate this so that this is like a circle, so if I rotate this around so it's sort of elliptic, right? We call this point here a saddle point, because it's not necessarily a local maximum. It's not really a local minimum either. It's its new kind of point, like a saddle almost. Okay? And if d is equal to 0, then our test is inconclusive. So let's try an example. So I'd like us to find the extrema and classify the extrema of the following function, such that f of xy is equal to x fourth plus y fourth minus 4xy plus 1. Okay? So to do this, we want to find our partial derivatives and set them equal to 0. So we get partial f partial x equals 4x cubed minus 4y. And we set it equal to 0. That gives us x cubed minus y equals 0. We can divide by 4, obviously. And that gives us y equals x cubed. Now remember this equation because we're going to plug this into our next equation. When we take the partial derivative with respect to y, we get 4y cubed minus 4x equals 0. And then we set that equal to 0, but we can plug in, for y, we can plug in y equals x cubed. So then we get x to the 9th minus x. Then we can factor and use your root theorem or whatever to determine that the solutions to this equation are -1, 0, and 1 for x. And then for y, you can plug in from our function to determine what the, you can plug in from this thing here to determine what your y values for the corresponding x points are going to be. And you get that they're going to be the same. So you get the points -1, -1, 0, 0, and 1, 1 as your three options for your critical points. So now what we will do is we will plug this into our theorem. So if I take the squared, I will gather all of my partial derivatives that I need. If I take the partial derivative with respect to x of f twice, then I will get 12x squared. If I take the partial derivative with respect to x and then y of f, then I get -4. And then if I take the partial derivative with respect to y 2 times of our function f, then I get 12y squared. So this means that, of course, dxy is equal to partial squared x of f times partial squared y of f minus partial squared of, or minus partial xy of f squared. So what we get is we get 144 x squared y squared minus 16. Plug that into our first candidate point, then d of -1, -1 is 128, which is greater than 0, and our partial derivative with respect to x twice at -1, -1 is 12, which is greater than 0. So by our classification, we now have a local minimum at -1, -1. And you can plug -1, -1 into your into the rule of our function, and you can determine what the value is. But if you want to graph it, although we should really leave the graphing of these multivariable functions to computers. Now, if we find d at 0, 0, I get -16, which is less than 0, so that means that I have a saddle point there. And then if I take d at 1, 1, that's going to be 128, which is greater than 0. And if I take the partial derivative with respect to x twice there, then I get 12, which is greater than 0. So then I have another local minimum. So you can see what this function looks like. So obviously here we have our one of our minima and another one of our minima, and then here we have our saddle point. All right, so that is the second derivative test and how you can classify these extrema. It's very helpful, and you can also find what the extrema are. So in the next video, we are going to use this knowledge to do some multivariable optimization problems, and then we'll look at absolute maxima and minima to round off our study of these properties of multivariable functions. All right, thanks for watching, and we'll see you in the next video. Bye.